Hello everyone, my name is Kwa, and today I'm presenting a paper called Interpretable Graph Similarity Computation via Differentiable Optimal Alignment of No Embeddings. So this is joint work with my collaborators, Saurabh Manjanda, Sujismit Mahapatra, and my advisor, Professor Jenna Reddy. So the problem that we consider in this talk is calculating the similarity between two graphs. Specifically, given a graph GA and a graph GB, we want to find we want to compute the similarity score S, where S is 1 if GA is exactly the same as GB, and is 0 if GA is very different from GB, and everything else is in between. So this task has several important applications in domains such as intrusion detection, drug design, software security, and so on. For example, in intrusion detection, its program is represented as an execution graph, and then for a query graph, we typically find a non-malicious graphs that are similar to the query graph in order to determine whether the program is an intrusion. Similarly, in social network, we also want to find people with similar behavioral patterns, where the pattern is represented by the graph of the user's activities. Finally, in the increasingly more important chemical domain field, the problem of finding molecules with similar graph structures is also an important problem. So depending on the domain, there's different ways to define the similarity between the two graphs. However, there are two important similarity measures called the graph edit distance, or GED, and a maximum common subgraph, or MCS. They are important measures because they are application agnostic and they are widely used in several domains, including those that we discussed in the previous slide. So GED is similar to the notions of string edit distance that I think most of us are familiar with. While string edit distance compute the cost of transforming one string of text into another string of text, GED compute the cost of transforming one graph into another graph. For example, to transform the left graph to the right graph, we first need to delete one node and two edges, and then replace one node, and then finally add one edge. So this series of edits quantify the GED, and because of the explicit explanations, GEDs are preferred measures in domains where we not only want to compute the similarity, but also want to capture the reasoning behind the similarity score. So to compute the similarity such as GED, especially the GED, there are previously two classical approaches. So the first approach computes the exact GED and is based on combinatorial search algorithms such as A*. And this approach, however, is NP-hard and is impractical for graphs with more than a few tens of nodes in practice. So the other approach is to approximate the GED using greedy bipartite algorithms such as the Hungarian algorithm. So these approaches are more efficient, but they are limited to only the GED computations, and they can have poor approximation quality in certain cases. So recently, there are some learning-based methods that approximate the similarity via trainable models such as GNN. Essentially, the learning process in this model is divided into two steps. In the first step, the representations of the nodes are extracted via models such as GCN. And in the second step, the similarity score is approximated via the function on the sets of node embeddings of the two graphs, as in the left figure, or as the function of the graph embeddings as in the right figures. And note that the function on the nodes embeddings is an ordering invariant functions. And the graph embedding is usually created on some ordering invariant functions of the nodes, as you can see. And as you can see, that this second strategy is simply a special case of the first one. So why this method works well in practice, there are some important limitations. First, the models are based on some heuristic assumptions and do not capture or explain the edit operations of the GED. Similar to the edit sequence example that I provided previously. Second, to achieve the best result, the method violates the ordering invariant constraint, and therefore the performance can be sensitive to the specific choice of the ordering in practice. Note that graph matching approaches can also be related to our works. However, none of the existing graph matching approaches can provide a suitable explanation for the GED. This is mainly because they do not learn the bijective mapping functions unless the node corresponding between the two graphs are provided for. So to solve the limitations of the previous approaches, we propose a graph optimal transport model for the similarity computation task. Specifically, this is the overall architectures of the model. So first, in this model, for each graph, we extract the node embeddings using embedding techniques such as CCN at each of the multiple levels of propagations. And then at each level, we compute the optimal assignment cost between two sets of node embeddings. And note that this optimal assignment cost is an ordering invariant functions of the node embeddings. And finally, the similarity score is approximated via the functions of the linear combinations of these costs. And given these techniques, we can learn node alignment that looks similar to this, which I'm going to go into detail in one of the later slides. So to compute the optimal assignment cost at each level of the GCN, we first define the following cost matrix C, where each entry in C represents the cost of transforming a node in one graph into another node in the other graph in the embedding space. One example of this pairwise transformation cost is the cosine distance between the two embedding vectors. So given this matrix, the optimal transformation cost can be formulated via this linear programming objective, where the goal is to find the optimal matrix M that result in the optimal transformations of the nodes from one graph into the other node in the other graph. Corresponding, we can also compute the gradient of this cost as well, as shown here. However, this formulation has two problems. So the first problem is that the similarity only defines the transformations, or the cost matrix only defines the transformation from one node to another node in the other graph. But we also need the cost for node addition and deletions as well. Second, these solutions and the gradients of the LP formulations are highly unstable, which make the gradient-based learning very challenging to solve this approach. So to learn this model, so to solve the limitations of the previous approaches, we propose a graph optimal transport model for the graph similarity computation task. So here is the overall architectures of the model. First, for each graph, we extract the node embeddings at multiple levels of propagations. For example, using the GCN. And then for each level, we compute the optimal assignment cost between two sets of node embeddings. Notice that these functions, this is the functions of an ordering invariant functions of the node embeddings. And finally, the similarity is approximated with the functions of linear combinations of these costs. So to compute the optimal assignment cost at each level of the GCN, we first define the following cost matrix C, where each entry in C represents the cost of transforming one node in one graph into another node in the other graph in the embedding space. One example of this pairwise transformations cost is the cosine distance between the two embedding vectors. Given this matrix, the optimal transformations cost can be defined as finding the optimal matrix M that transforming the nodes on one graph into the other node, the nodes in the other graph via the linear programming objective. Correspondingly, we can also compute the gradient of this cost as well. However, this formulation has two problems. First, the cost matrix only defines the transformation from one node in one graph to another node in the other graph. But we also need the cost of node deletions and deletions as well. And second, this solution and the gradients of the linear programming objectives are highly unstable, which makes the gradient-based learning very challenging to be used in order to learn the parameters of the model. So for this reason, we propose to extend the previous rectangular matrix into a square matrix, where we add two additional blocks. So the block on the bottom left is responsible for node additions in the first graph, while the one on the top right is responsible for the deletions of the node also in this graph. And these costs can be constant cost or can be calculated based on the GCN representations of the nodes. But the constant cost results in more hyperparameter tuning. And for such reasons, we employ the second approach where we automatically learn the parameter of node additions and deletions. Specifically, we define two global embedding vectors at each of the GCN level that are responsible for node addition and node deletion correspondingly. And based on these embedding vectors, the addition and deletion cost is the functions of the specific node and the node embedding, the global embeddings. So given this square matrix, it turns out that its linear programming objective amidst a permutation matrix M is the solutions. And we can show that the solutions, as well as gradients, are stable. But more importantly, the gradient is similar, where we just multiply the gradient of the cost matrix with the optimal matrix M star by solving this linear programming objective. So for the rest of the talk, we will show the effectiveness of our solutions in empirical experiments. Specifically, we consider multiple tasks, which is based on the graph similarity, including the approximation task of GED and MCS, and the similarity search and ranking tasks based on these similarity measures. So we use 4 different data sets from different domains, including the data sets from the chemical domain, such as ETS and BTC, and from the software security domain, such as Linux, and one data set from representing the ego networks of actors called IMDb. And the number of graph pairs in these graphs range from 100,000 pairs to 2.25 million pairs. So for the approximation task, we use MSE and MAE as the metrics for evaluations. For the ranking task, we consider correlation metrics such as Spearman and Kendall tau, and also the precision at K. So we compare our approach against several classical algorithms, including the approximate bipartite algorithms, Hungarian and Horsdorf. For learning based, we consider the graph similarity approaches, which are based on the graph embeddings, where the graph embedding is created based on the invariant mean, max, and gauge functions of the node embeddings. And also the SOTA state-of-the-art method in this category called SimGNN. For node embedding, we consider GraphSim, which is the state-of-the-art method for the similarity computation task. We also consider a notable graph matching method called GMN, or graph matching network, which has been previously used to approximate the similarity. So for the GED approximation task, our method GED-SIM achieves the best approximation error, as you can see in this table. Note that for ETS and Linux, since the number of nodes in these graphs are small, we can compute the exact graph root, which is based on using the A-star algorithm. While for BTC and IMDb, the number of nodes are much larger, so that we can only approximate the graph root GED by the combinations of bipartite and Horsdorf algorithms. So these algorithms essentially set the optimal results for the task. We can see that our methods performs better than all of the methods when the exact graph root are available, while very close to the best classical approximate space lines when the graph roots are missing, the exact graph root are missing. And we can also observe very similar results for the MCS approximation task, which you can find in the paper. So similarly, our method outperforms other methods in the graph retrieval and ranking task in all of the correlation and precision metrics. And we can see some of the example of the sample queries and their top K results. Essentially, our methods retrieve graphs that are very similar to the graphs retrieved by the A-star algorithm in this example. And we also attempt to look at the learned graph alignments in our method. And we can see that the top example show the graph alignment for 2 isomorphic graphs. You can see that our methods recover the exact alignment is that of the A-star algorithm, where the bipartite matching algorithm fails to do so in this case. We can also see similar observations for the multi-label case, and is in the middle figure, where GED-SIM captures also very similar alignments is that of the A-star algorithm. So in conclusion, we propose a learning-based graph similarity method called GED-SIM. Essentially, in this approach, the graph similarity is approximated by a differentiable minimal transformations cost from one node into another node. The method can be used with any existing GNN-based embeddings methods besides GCN, and we see show that GED-SIM achieves state-of-the-art performance on both graph approximation and retrieval ranking tasks. we can show that GeoTSIM results are interpretable, and we can visualize the learned knowledge science between the pair of graphs, in addition to the similarity score. And for such reason, you can see that GeoTSIM can have very useful applications in domains where explainable alignments or sequence of edits are required, along with the similarity score. So thank you for listening to our talk, and this is our contact information, and you can also find the code in this GitHub tables.